Welcome back to the Deep Dive. Today we're doing something a little different. We're not just analyzing engineering, we're looking at a surgical strategic blueprint.
That's a great way to put it. We're tackling one of the biggest challenges you can face in university racing. Building a world-class Formula Student electric powertrain, an FSE car, from a totally blank sheet of paper.
And the document we're working from, this Statement of Requirements, or SOR, it's not your typical student project plan.
No, not at all. This was clearly put together by a senior powertrain architect, and they've used this really rigorous professional framework, the kind you'd see at a top consulting firm like McKinsey.
The MBCE framework, right?
Exactly. Mutually exclusive, collectively exhaustive. Every requirement is distinct, and together they cover everything. The goal isn't just to build a car that runs.
No, the mission is incredibly aggressive. Most new teams, start small. They'll aim for a 300-volt, maybe a 400-volt system.
Sure, a safer route.
Exactly. This team is trying to skip that whole painful 4-year learning curve and go straight for the top. They're trying to challenge the current world champions, the teams like AMZ or TU Delft that dominate Formula Student Germany.
Which is an incredibly high-risk, high-reward strategy. And that goal, that ambition, forces two non-negotiable architectural decisions right from the get-go.
And these two decisions define the entire car.
They do. First, a 600-volt high-voltage platform. And second, a four-wheel drive or 4WD in-wheel motor topology.
You choose those two things. And you are committing to world-class performance, but also
world-class complexity, absolutely.
So that complexity, it only really makes sense if the performance targets are just as aggressive. Let's dig into the KPIs, the key performance indicators that this strategy demands.
Yeah, and these are brutal. They're basically reverse engineered from what the champion teams are doing. First, peak power. The rules hard limit you to 80 kilowatts.
And that has to be software controlled with, absolute precision.
Oh yeah, scrutineers will check. But power alone is nothing without grip. So to win the acceleration event, which is the big 75-meter sprint, the total wheel torque has to be over 1,200 Newton meters.
Over 1,200. And what does that number actually get you on the track?
That is what you need. It's the minimum to guarantee a sub 2.5 second 0 to 100 kilometer per hour time.
And that 2.5 second barrier is really the competitive benchmark.
It is. If you're slower than that, you're already out of the running for a top spot in that event.
Okay, acceleration's one thing, but this relentless focus on mass reduction.
Yeah.
That's where the high voltage choice really starts to pay dividends, right?
Absolutely. The target for vehicle mass is under 200 kilograms.
And that's not just the chassis. That's with the full aero package, right?
With everything. The wings, the undertray, everything. And when you combine the 80 kilowatt peak power with that sub 200 kilogram mass, you're gunning for a power to weight ratio of over 400 kilowatts per ton.
That's hypercar territory.
And then you have efficiency, which is critical for the main event, the 22-kilometer endurance race.
Right, you can't just be fast, you have to be efficient.
Exactly. The strategy demands a very high level of regenerative braking. The recuperation rate, so the energy you get back into the battery when you brake, it has to be greater than 60%.
And every watt hour you recover is one you don't have to carry in the battery.
Which directly cuts down your mass. It's all connected.
But there's one KPI in here that's maybe the most important for a new team, and it's the one that, students focused on speed can sometimes forget.
And that's the 100% endurance race completion rate.
100%.
The data is so clear on this. New teams, they fail to finish the endurance event maybe 40–50% of the time. If you don't finish, you score 0 points for the biggest event of the weekend. Your season is sunk.
So the strategy document puts it in bold, basically.
It does. Reliability trumps peak performance. You absolutely have to finish before you can even think about winning.
Okay, so let's unpack that foundation. We have the targets,
Yeah.
200 kilos, 80 kilowatts, 1,200 Newton meters. But why? Why pick the two hardest technologies, 600 volts and 4WD, to get there? It just seems like massive engineering overhead for a brand new team.
It's a calculated risk. It's about skipping the incremental steps. The whole idea is to leverage fundamental physics and vehicle dynamics that, simpler, lower voltage cars just can't match.
You're trading mechanical simplicity for electronic control.
Exactly. Let's start with that 600-volt choice. What is the core physical payoff that makes all the danger and complexity worth it?
Yeah, what's the big prize?
It all boils down to one simple equation from physics, the I²R payoff. It's about managing heat loss.
Joule heating.
That's the one. Let's just run the numbers. The rules cap us at 80 kilowatts of power. Now, If the team went with a conventional, safer 300-volt system, that 80 kilowatts would mean the system has to handle about 267 amps of current.
Which is a huge amount of current. That's a ton of heat to manage.
A ton? And that heat is the enemy. So here's the insight. Our mandated 600-volt system only needs half that current, around 133 amps, to deliver the same 80 kilowatts of power.
And because the loss is proportional to the current squared.
Bingo. You have the current and the thermal power loss across the entire system. In the battery, the bus bars, the inverter, it drops to just 25% of what the 300-volt system would generate.
A quarter of the waste heat.
Just a quarter. That is the strategic knockout punch.
That must change everything for the engineering teams.
It fundamentally simplifies the design of 3 major mass-intensive subsystems. First, battery cooling. Way less internal heat, so you need a much simpler, lighter liquid cooling system. Second, the inverters need smaller, lighter heat sinks.
And the third?
The wiring harness. This is a big one. A 300-volt harness that can safely handle 267 amps. I mean, you're talking about copper cables, maybe as thick as your thumb. They weigh kilograms.
Right.
The 600-volt system can use much thinner, lighter wiring, maybe the size of a pencil. You can instantly save 5 or 6 kilograms right there. And since mass is everything for power to weight, the 600-volt choice becomes the ultimate mass-saving strategy.
Okay, so the trade-off is clear. You accept the complexity of maintaining perfect high-voltage isolation, and in return, you get this massive weight-saving and simpler cooling.
Provided you nail the compliance and safety, yes, it's a huge physical advantage.
So that's the electrical side. Now let's pivot. The 4WD necessity. Why can't we just use a simple, powerful, single-motor rear-wheel drive setup?
I mean, RWD is simpler, right? It's lighter, easier to package.
So why is it limited in FSE?
It just hits a physical wall, especially in the dynamic events like the skid pad, that's the figure 8, and the autocross course.
Because of the friction circle of the tire.
Exactly. Every tire has a limited amount of grip. It can be used for turning, so lateral force, or for accelerating and braking, longitudinal force. When you're cornering really hard, say at 1.5 Gs, your tires are already using most of their available grip just to turn the car.
So if you're in an RWD car and you hit the gas mid-corner,
You instantly exceed that friction circle. The rear tires have to provide both the turning force and the acceleration force. It's too much. The rear end slides out or you just get wheel spin. You're traction limited.
and 4WD with 4 independent motors breaks that limit.
It shatters it because we can use torque vectoring. With independent motor control at all 4 corners, the software can dynamically shift torque between the left and right sides and front to back.
So you can generate a turning force without actually turning the steering wheel more.
Precisely. By applying what we call asymmetric torque, say, powering the outer wheels more and maybe even slightly regenerating on the inner wheels in a turn, the system generates an additional yaw moment.
A turning force.
Think of it as a ghost turning force, controlled entirely by software that actively pulls the car's nose into the corner. It's more than the mechanical steering can do on its own. It is, basically, software-defined grip.
That has to be a game changer for lap time.
It's decisive. It dramatically improves cornering speed and allows the software to instantly correct for understeer or oversteer. The RWD car has a performance ceiling. The 4WD car with torque vectoring has a fundamentally higher one.
The classic counterargument, though, is unsprung mass. If you stick a motor, a gearbox, a brake assembly on all 4 corners, surely you're going to blow past that 200-kilo limit instantly.
And that leads us right to the core of the in-wheel design philosophy. Since we can't compromise on mass, the strategy mandates these highly integrated in-wheel power units.
So you're packaging the entire powertrain inside the wheel assembly.
Yes, the complexity shifts from the overall system architecture to extreme component miniaturization. The whole unit, the motor, the specialized planetary gearbox, the brake system, it all has to be packaged to fit inside a tiny 10-inch carbon fiber rim.
Which is an absolute mechanical engineering nightmare.
It is. But it's the only way to get the 4WD advantage without killing the car's dynamic response with too much unsprung mass.
Okay, let's shift from the why to the how. Risk mitigation. We're committed to this 600-volt system. That is a lethal voltage. How does this spec ensure compliance and, more importantly, safety, especially with the tough scrutineering at places like FSG?
Yeah, this section is all about building in safety margins. The rules are hard limits. You ignore them, you get disqualified instantly.
So let's talk about the biggest trap, the 600-volt compliance trap.
Right. The rule is EV 4.1.1. It says the maximum voltage between any 2 points cannot exceed 600 volts DC. The fatal mistake a lot of new teams make is they design their system with a nominal voltage of 600 volts.
And simple math tells you why that's a disaster.
Exactly. A standard lithium-ion cell, when it's fully charged, is at 4.2 volts. If a team uses, say, 144 cells in series of 144s pack, the math is 144 times 4.2 volts, which equals 604.8 volts.
And that 4.8 volts over the limit gets you sent home.
Immediately. Your competition is over. So the strategic directive is crystal clear. You have to mandate a 140, so 140 series cell configuration. The maximum voltage then is 140 times 4.2, which is 588 volts.
Which creates a vital 12-volt safety margin.
A 12-volt buffer. And it's not just for static compliance. During heavy regenerative braking, you get these voltage spikes and ripples as energy floods back into the pack. If you're sitting at 599 volts, a tiny regen spike pushes you over 600. That 12-volt margin absorbed those dynamic events.
That makes sense. Okay, so that's the voltage managed. What about physical protection, the IT system and isolation?
Right. The system has to be what's called an IT system, or isolator. It means the entire high-voltage circuit is completely galvanically isolated from the car's chassis, from ground.
So if one wire touches the chassis, it doesn't create a short circuit?
Not immediately. But the system has to detect that loss of isolation and shut down before a second fault could create a disaster. This means we have to use shielded cables for the main HV bus, and the shield has to have a perfect 360-degree ground termination. It acts like a Faraday cage.
Preventing EMI, electromagnetic interference.
Right. It stops the high-frequency noise from the inverters from messing with all the low-voltage control signals. And every interface between the high-voltage and low-voltage world, say the VCU talking to a sensor, has to use an optocoupler or a digital isolator with at least a 2.5 kVRMs rating.
So you need systems to protect the components during power up and power down too. Pre-charge and discharge circuits.
These are essential. When you first turn the car on, if you just close the main relay, you're connecting this massive battery pack to a bank of empty capacitors in the inverters.
Which act like a short circuit for a split second.
Exactly. The inrush current is enormous. It can weld the relay contacts shut or just destroy the capacitors. So the pre-charge circuit uses a resistor to gently charge those capacitors up to over 95% of the battery voltage before the main relay closes.
And there's a time limit on that.
Yep, it has to be done in 1 to 3 seconds. Too fast, you overheat the resistor. Too slow, the driver can't launch. You have to spec a special resistor that can handle that energy pulse, which is around 180 joules in this case.
And on the other side, the discharge circuit.
The rules are strict. The bus voltage must drop below 60 volts within 5 seconds of shutdown. This is for the safety of first responders. You can't rely on the inverter's internal logic for this.
You need redundancy.
You need a separate hardware discharge circuit, usually a normally closed relay that, when power is cut, springs shut and dumps the capacitor energy through a big resistor. Fail-safe.
Okay, now the active safety systems.
Yeah.
The IMD and the HVIL.
The insulation monitoring device, the IMD, is the heart of the IT system safety, and for this, the strategy is blunt. Mandate the industry standard, the Bender isometer, ISO 165C.
Because that's what the scrutineers know and trust.
Exactly. Don't give them a reason to question your safety case. The threshold is set based on the voltage, so for our 600-volt system, it has to trigger a fault if the insulation resistance drops below 300 kiloohms.
And then there's the HVIL, the high-voltage interlock loop.
This is the physical safety chain. It's a low-voltage loop that runs through every single high-voltage connector and access panel. If any of them are opened, the loop is broken.
And you have to use special connectors for this.
You do. They have to have a last mate first break design. The HVIL pins are physically shorter than the high-voltage power pins. So if someone tries to unplug a live connector, the HVIL connection breaks first.
The VCU sees that break.
And it has less than 10 milliseconds to open the main relays, cutting all the power. This ensures the high-voltage terminals are de-energized before they can physically separate and create a dangerous arc. It's the ultimate protection against human error.
Okay, let's get into the components. The energy storage system. We've established it's all about power density over energy capacity. So what cells did the architect actually choose?
The cell choice is purely strategic. It's about maximizing current delivery and minimizing heat. We're looking for the lowest electrical impedance we can get.
So what was on the table?
Well, we looked at the legacy standard, something like the Sony VTC6. It's an 18650 cell, it's proven, but it has higher internal resistance. The strategic decision here is to mandate the current performance benchmark, the Molicel INR 21700 P45B.
The P45B, what makes it so much better for this application?
Two things. First, the 2020-C100 format is physically bigger than the 18650, which helps with heat dissipation. But the real key is its incredibly low DC internal resistance, or DCIR. It's down around 15 million.
And that's critical because of the I-squared-R losses we talked about.
Exactly. Lower internal resistance means less voltage sag under load, so more consistent power, and crucially, less heat generated inside the cell itself. We're already at low current because of the 600 volts, and this just minimizes the thermal stress even further.
So what does the final pack topology look like?
The configuration is 140's 3P, so 140 cells in series, with 3 of those strings in parallel. That's 420 cells total.
And the energy capacity?
Comes out to about 6.8 kilowatt hours.
Which seems like a lot. The endurance race only uses maybe 4.4 kilowatt hours. Is that extra mass a penalty?
It's not a penalty, it's a strategic buffer. That 50% extra energy ensures you can finish even with a high-drag aero package. It accounts for cell aging over the season. And most importantly, it means you never have to run the cells down into their low state of charge, high-resistance zone. You preserve peak power and thermal stability for the whole race.
Makes sense. Now, managing 140 cells in series requires a really sophisticated battery management system, a BMS.
You can't use a single chip for that. You have to go with a distributed master-slave architecture. So you have slave boards distributed throughout the pack, each monitoring a small group of cells.
And the hardware for those slaves.
The mandate is for the Analog Devices LTC6813 chips. They're proven, they're accurate, and each one can handle 18 cells, which is a good number.
Communication in that noisy 600-volt environment must be a nightmare. How do you guarantee the data from the slaves gets to the master reliably?
Right. A traditional CAN bus would just get drowned in EMI. So the strategy mandates ISO SPI. It's an isolated SPI protocol that uses twisted pair differential signaling. It's extremely robust against noise, way better than CAN for this job.
And for the master unit itself, the choice is a commercial one, the Orion BMS-2, not a custom student design. Why?
For a new team at 600 volts, stability and reliability have to be the primary goal. The Orion is proven. It has complex fault diagnostics and reliable state of charge estimation right out of the box. Building a custom BMS that could pass scrutineering might take a team 2 years. Mandating the Orion basically buys them that time. It minimizes risk.
Okay, thermal management. We know air cooling is out. What's the liquid strategy?
No, air cooling is a non-starter. The mandate is for liquid cold plates. We're talking aluminum serpentine flow channels that sit between the rows of cells.
But the cells are round and the plates are flat. How do you get good thermal contact?
You have to use a high-conductivity thermal interface material, or TIM. In this case, GAT pads. They fill that void and create a really efficient heat path from the cell casing to the cold plate.
And what's the performance target for that system?
The requirement is that CFD simulations have to prove the maximum temperature difference between any 2 modules is less than 5 degrees Celsius. Consistency is key. The BMS has to monitor at least 30% of the cells, and the system starts deaerating power at 60 degrees with a hard shutdown at 70 degrees C.
And finally, the rules require the pack to be segmented for safety.
Yeah, this is purely for safe handling. Each segment has to be under 120 volts and under 6 megajoules.
So how does our 140s pack fit that?
We divide it into 5 independent modules. Each module is 28 cells in series, 3 in parallel, so 28's 3P.
And the math on that works out.
It does. 28 times 4.2 volts is 117.6 volts, safely under the 120 volt limit. And these modules are connected with big, toolless maintenance disconnects. It means a student working on the pack is only ever exposed to a maximum of 117.6 volts, which is a huge safety improvement.
All right, we've got the power stored safely. Now we have to get it to the ground. Since the choice was 4WD in-wheel motors, what are the specific drive units that get you to that world-class benchmark?
Well, for a new team, trying to develop your own motor is a project killer. It's a massive distraction.
So you buy off the shelf.
You adopt the industry standard used by the top European teams, the AMK DD51410 TOW. It's a permanent magnet synchronous motor.
And what are its specs? Why this one?
It's liquid-cooled, it's compact, and it's optimized for speed. It'll give you about 35 kilowatts peak power, and it spins up to 20,000 RPM.
Okay, but you said it's optimized for speed. What's the torque like?
And that's the challenge. The direct torque output is really low, only about 21 Newton meters.
And we need 1,200 total at the wheel, so that's a huge problem.
It is. This is where the mechanical team has to be world-class. Because it's a high-speed, low-torque motor, it requires a mandatory, very robust planetary gearbox. The spec calls for a reduction ratio somewhere between 12 to 1 and 14 to 1.
So the gearbox is just a torque multiplier.
That's all it is. With a 12-to-1 ratio, that 21 newton meters becomes over 250 at the wheel, times 4 wheels, and you're over 1,000. The 14-to-1 ratio gets you closer to that 1,200 newton meter target.
I have to ask, if we're so worried about mass and complexity, why not skip the gearboxes and just use a lower speed, higher torque, direct drive motor?
That's a great question. It's a common debate. And the answer is inertia. A direct drive motor that makes that kind of torque at low speed has to be physically much larger, much heavier, and have significantly higher rotational inertia.
Which would make the car feel sluggish.
Exactly. It hurts the car's dynamic response. By using a small high-speed motor with a gearbox, we minimize that rotational inertia on the unsprung side of the suspension, which is critical for handling. We're trading mechanical simplicity for better dynamics and lower mass.
That makes sense. Okay, what about the power electronics that feed these motors? The inverters.
Yeah, this is where the 600-volt choice really gets maximized. The strategy mandates a technology shift to silicon carbide, or silicon MOSFET inverters.
Why Sison instead of the traditional silicon IGBTs?
6 is just a fundamentally better material for high-voltage, high-frequency switching. 6 devices have dramatically lower switching losses. The efficiency gain is huge. You go from maybe 95% with IGBTs up to 98-99% with 6.
And that efficiency gain translates directly back into mass reduction.
It does. Less waste heat means you need smaller, lighter heat sinks. It reduces the load on the whole electronics cooling system. It's another one of those cascading mass savings that starts with the 600-volt decision.
And what specific inverter is recommended?
The AMK KW26 S5 FSE 4Q. This is a dedicated 4-in-1 solution that's specifically tuned by the manufacturer for those AMK DD5 motors.
And that's a huge time saver for a new team.
It's the single biggest time saver you can buy. It comes with preset magnetic flux maps for the motors. Mapping a motor yourself is a horribly complex 6-month-long process on a dyno. This purchase buys the team 6 months of development time. It's invaluable.
What about the control strategy inside the inverter?
It uses field-oriented control, FOC, for the basic torque control. But the key capability for top speed is field weakening. As the motor spins faster, its internal voltage, the back EMF, rises. If that back EMF gets close to the 600-volt bus voltage, the motor can't accelerate anymore.
So field weakening is a way to cheat that voltage limit.
In a sense, yeah. You inject a negative current on what's called the D-axis, which effectively weakens the rotor's magnetic field. This lowers the back EMF and allows the motor to keep accelerating, extending its speed range from its base RPM of, say, 12,000 all the way up to its 20,000 RPM max. It's how you get both incredible acceleration and a high top speed.
We've got the hardware sorted. But the real magic of 4WD, the torque vectoring, that's all software. And at 600 volts, a single software bug could be, well, catastrophic. So what defines a winning and a safe control system?
The control system is where the real competitive edge lies.
Yeah.
And the complexity here demands robust hardware for the VCU, the vehicle control unit, and an even more robust automotive-grade development process.
Let's start with the brain, the VCU.
It has to be a high-performance real-time platform, something like an STM32H7 or a D-Space micro-auto box if you have the budget. And to handle all the data, we're mandating a minimum of 3 segregated CAN-FD buses.
CAN-FD for the higher data rate. But why segregate them?
To prioritize critical data, you have your power CAN, which is for high-priority, low-latency torque commands to the 4 inverters, then a sensor CAN for the IMU, pedals, steering, and a data logging CAN. The key metric is that the power CAN bus load has to be kept below 60%.
To guarantee latency.
To guarantee that a critical torque command, like from the traction control, has a latency of less than 1 millisecond. Any delay there makes the car feel unstable and slow.
So let's talk about that core advantage, the layered torque vectoring algorithm. How does the software actually turn a steering input into that magic turning force?
It's a 3-layer control hierarchy. The first layer is the reference generation.
What does that do?
It calculates the ideal vehicle behavior. So the desired yaw rate, based on the driver's steering angle and the car's speed. It's basically a mathematical model of the perfect cornering line.
Okay, so that's the target, layer 2.
Is the high-level controller. It compares that desired yaw rate to the actual yaw rate, which it gets from the car's IMU. The difference, the error, is then used to calculate the correcting yaw moment needed to get the car back on the ideal path.
And the final layer sends that command to the wheels.
Right, the low-level allocator. It takes that required yaw moment and translates it into individual torque requests for the 4 motors. You know, more torque on the outside wheels, less on the inside. But, and this is critical, before those commands go out, they have to pass through the power limiter module.
To make sure you don't exceed the 80 kilowatt rule.
At any instant, it sums the requested power for all four wheels and makes sure it's always under 80 kilowatt.
Torque vectoring helps you turn, but you still need traction control for going straight.
Oh, absolutely, especially with the instant torque from a 600-volt system. The strategy here is slip ratio control. The VCU constantly monitors the difference between the wheel speed and the vehicle speed for each tire.
The slip ratio.
And if that slip ratio goes above an optimal limit, say 15 or 20%, the controller has to instantly cut torque to that specific wheel to regain grip. Without it, you just can't put the power down.
The software controls performance, but it also is the safety system. So this mandated V-model development process seems like the ultimate quality gate.
It's non-negotiable. It's forcing the team to adopt the same process the real automotive industry uses, aligned with ISO 26262. It's designed to stop software bugs from becoming hardware failures.
Let's talk about the validation side of that V. It starts with MIL, model in the loop.
Right. This is where you build mathematical models of everything, the motors, the tires, the chassis, in something like MATLAB Simulink. You test the logic of your torque vectoring and traction control in a purely simulated environment. Then, critically, you use automated code generation to turn that validated model directly into C code, which eliminates human coding errors.
And then comes the most critical step before you touch any high-voltage hardware. HIL testing, hardware in the loop.
HIL testing is the single most important safety investment this team will make. You take the actual physical VCU that will run the car and plug it into a real-time simulator.
So you're testing the real brain against a virtual car.
Exactly. The simulator mimics the motors, the BMS, the sensors, even communication faults with microsecond accuracy. It lets you test the most extreme failure modes. What happens if a sensor disconnects at 100 kilometers an hour? All in the safety of the lab. You validate the functional safety before you ever connect a live battery.
Which brings us to the mandatory safety logic that has to be coded into that VCU, the fault response matrix.
Yeah, you need a robust state machine with very clear, defined responses.
So what are the hard stops? The most severe faults?
If the HVIL loop opens, meaning a high voltage area is exposed, or if the BMS reports a critical cell over or under voltage, that's an immediate hard shutdown. The VCU has to cut power to the main errors instantly.
What about driver error, like hitting the brake and throttle at the same time?
That's the brake system plausibility device, or BSPD. If the system sees high brake pressure and a high motor power request at the same time for more than a fraction of a second, the VCU has to cut the inverter enable signal, then the ARs. It prevents the car from running away if a sensor fails.
And for less critical issues.
Like a single sensor giving bad data, the system enters limp mode. It restricts all the motors to a very low, safe torque level, maybe 5 Newton meters, enough for the driver to safely pull off the track.
Okay, so we have this incredibly complex, aggressive, but strategically sound architecture. How do we actually prove it all works? And how do we make sure it passes the final technical inspection at these global events?
Well, proof is in the testing. And compliance is all about anticipating what the scrutineers are going to look for. You have to validate every single subsystem before you dare to integrate them.
What are the mandatory physical tests for the battery pack?
First, single-cell testing. You can't just trust the manufacturer's datasheet. You have to take your actual Molicel P45B cells and test their discharge curves at different temperatures. That empirical data is what you use to build an accurate open-circuit voltage to state of charge lookup table for your BMS. Without that, your fuel gauge is just a guess.
And for the motors and inverters?
You need a proper powertrain dyno. You couple the motors and inverters to a load motor. This proves two things. One, that your lightweight cooling system can actually handle the heat under continuous load. And two, it lets you map the real-world efficiency of the whole system, proving that the I-squared-R gains you designed for are actually there.
Let's talk about a classic failure point, especially in Europe. The rain test.
Ah, yes. At FSG, your 600-volt car has to run in simulated rain for 2 minutes without the IMD tripping. This is where so many high-voltage teams fail.
So what's the design mandate?
Absolute. All HV enclosures, the battery box, the inverter cases, they all have to be rated to a minimum of IP65.
But the temperature changes create their own problem, right? The enclosures can breathe.
That's the subtle failure mode. The pack gets hot, then it cools down, the air inside contracts, and it sucks in moist air from the outside. That moisture condenses, the insulation resistance drops, and your IMD triggers a fault.
So how do you solve that?
You have to use specialized waterproof breathable vents, like Gore-Tex vents. They let the pressure equalize without letting moisture in. And of course, all your cable glands have to be IP68 waterproof.
And finally, this car needs to be globally compliant. One car for all competitions.
Right, so you design to the strictest rule set, which is usually FSGs. That means preparing your detailed structural equivalency documentation for the carbon fiber accumulator container, proving it's as safe as the default steel one in the rules.
And the visual safety systems can't be an afterthought.
No, the TSAL, the Tractive System Active Light, has to be bulletproof. It needs a high reliability circuit. Green for safe, blinking red for active high voltage. If that light fails, your car fails tech inspection. It's that simple.
So to synthesize this entire strategic document, the 600-volt 4WD architecture, it gives a new team all the physical potential they need for world championship performance. It's a massive head start.
Right. We've engineered in 3 core advantages: maximum efficiency and mass reduction from the 600-volt low-current 6E approach, superior handling from 4-wheel torque vectoring, and minimum vehicle mass from optimizing every single component.
But, and this is the big but, the crucial realization here is that success isn't determined just by picking these fancy components.
No, it hinges entirely on the execution of the development and validation process.
It's all about process control and risk mitigation.
Yes. Success depends on the team's strict adherence to that V-model development process and the mandatory, rigorous implementation of hardware-in-the-loop testing. At 600 volts, your control software is your safety system, and HIL is the only way to fully validate that safety logic before you put a driver in the car.
Which brings us to our final thought. We have engineered out the strategic hardware risk by mandating world-class components and world-class safety processes. But there's one final strategic element that separates the champions from everyone else.
And that is the digital twin.
If a team fails to invest the time up front to build a rigorous digital twin, a complete energy, thermal, and dynamic model of the entire car in software before they even start cutting carbon fiber,
the time they save by buying the right components will be lost tenfold in trackside debugging and expensive, catastrophic failures.
Every top team in the world lives in the virtual world first. The digital twin is the predictive model that catches the 144's cell trap, that tells you exactly where your battery will overheat, that validates your torque vectoring stability before you've even built a chassis.
It's the ultimate risk mitigation tool.
So the provocative thought for you to take away is this. Considering that I-squared payoff we talked about at the very beginning, how much time are you willing to spend simulating and perfecting that virtual model today to save yourself from very real, very expensive failure tomorrow?